My name is Max. I'm here to present two concurrent works, both at this conference. The former is by myself, Yuval, Kostis, and Noah. The latter by Bing Fei and Aviat. Check out both papers if you get a chance. Now, the main result of both of these papers is an algorithm for no swap regret, online learning with many actions. But what is swap regret? What's online learning? And why are there so many actions? We're going to answer all those questions here today. Stay tuned. Let's start with the basics of online learning. In the setting of online learning, we have a set of actions, and we're going to repeatedly choose an action. So at every single time step, we make a choice, and then observe the reward of our choice, as well as observing all the rewards of the choices we didn't make. So our goal is to repeatedly make these choices, adapt to the reward feedback that we receive. Also allowed for in this model is a selection of a distribution over actions, in which case our reward is the expected reward. So formally, every round we choose a distribution over n actions, an adversary selects a reward vector, and over capital T rounds of learning, we incur some total reward. Now, when we're evaluating the performance of an online learning task, the classic measure is regret. I'm going to start by defining regret in a very general way, and then we'll go through some specific notions of regret that you're perhaps more familiar with. But generally, regret is always going to be a comparison between the reward our algorithm obtains versus some sort of benchmark. Okay, what could that look like? So let's say we were doing some online learning task. We produced, capital T strategies, actions, received capital T rewards, incurred some total reward over time. What we're going to consider is a transformation mapping feat that maps our actions x1 to xt to some transformed actions phi of x1 to phi of xt. And then against these fixed history of rewards, we could think of the transformed reward of those actions. And regret is always going to be about comparing the reward we got to some sort of transformed reward. Namely, we're going to consider some sort of set of transformations, capital phi, and we're going to want our algorithm to get reward that's comparable to all of the possible transformed rewards in this set. So that's the general definition. Now, and then we also say that we get epsilon regret if this total, the comparison between any of these best transformations versus what we did is at most epsilon times t. Now, a classic form of regret is external regret, probably the one most of y'all are familiar with. In this setting, capital phi is the set of all constant maps. So that means that we hope that our algorithm gets reward comparable to the reward of any best fixed action in hindsight. Okay. But the goal of this talk is going to be to accomplish a stronger guarantee. I want to compete with a larger class of transformations, which is going to be a swap regret. And if we can compete with all of these possible transformations, we're going to get richer rewards. So under swap regret, the set of transformations is going to be all maps from the actions to themselves. I want to compete against all these transformations. So what could that look like? Let's say that we had some sort of history of play here, where there's some rounds we played action A, some rounds we played some action B. And let's say that we're pretty happy actually with the rounds where we played action A. We got a good amount of reward. But there's some rounds where we played action B where we actually ended up missing out on a lot of potential reward. So if this was the history of play, then we would have incurred a lot of swap regret. Because one potential transformation we'd have to compete against is a transformation where, these rounds where we played action A remain action A, but these rounds where we played action B get transformed to some action C that would have gotten much more reward. Okay? So that would correspond to this sort of transformation right here. Now, it's possible that this history of play actually got good external regret, because if we were to have to swap that rounds where we played B to rounds where we played C, we would also have to swap the rounds where we played A to rounds where we played C. Potentially, the loss of reward there wouldn't make up for the reward we gained. So you can see that swap regret is a strictly stronger, performance measure to hold ourselves to. But of course, we also contain within our set of swap transformations all the external regret transformations, all the constant mappings, as well as mappings where every single action goes to a totally new action, right? All of these transformations are going to be in our set. We want to compete well against all of these transformations. As I introduced this problem, I introduced it as, we select a distribution over actions every round. Here's an example where these are pure actions. This notion generalizes nicely to, rather than dealing with maps from pure actions to themselves, could be all transformations of linear transformations from the simplex over n actions to the simplex. In this work, we actually Get good performance compared to all possible maps from the simplex to itself, not even continuous ones. Absolutely everything, we do it. All right. So why swappergrad? Why should we hold ourselves to this stronger performance benchmark? There's a number of reasons. There's lots of different online performance measures which fall under the umbrella of swappergrad, like calibration. There's certain settings wherein external regret algorithms are exploitable by adversaries who know exactly what algorithm you're running, where swappergrad algorithms are robust. But I think the best way to motivate swappergrad is in the setting of games. So what does that look like? So let's say we have a game, like rock, paper, scissors. And let's say we want to compute like the optimal strategy in this game. One thing we could do is we could instantiate a no-regret learner for each player in the game and have them repeatedly choose actions. We have this guarantee that, if these people choose actions for capital T rounds, we have a guarantee that if we had initialized these learners as no external regret learners, then their time average strategies are going to converge to something that is known as a course correlated equilibrium. Whereas if we instantiate these learners with a stronger no swap regret guarantee, we have a guarantee that their time average strategies converge to something that is known as a correlated equilibrium. So just really quickly kind of what those mean, an equilibrium in a game is some sort of strategy profile where no player wants to deviate, okay? And what I mean by deviate is going to depend on what sort of equilibrium I'm talking about. So what that means is, like let's say we have two players here, and I recommend that this player play action A and this player play action B. This player would want to deviate if he'd say, I actually don't want to listen to you, Max. I'd rather go with some other action C instead. So a player would want to make a course deviation if they would say, you know what, no matter what you tell me, I'm going to totally ignore your recommendation. No matter what, I'm going to want to deviate and play this particular fixed action C. Whereas the set of swap deviations, the larger set of deviations, entails players who could perhaps deviate conditional to the recommendation that I give them. They could, I could tell them to play action A, and they'll be like, all right, I'm happy to play action A, I'll stick with that. But, conditional on the fact that you're telling me to play action B, okay, I'd actually rather deviate, play something else. So this is a larger set of deviations. Course correlated equilibrium is only robust to these course deviations, whereas correlated equilibrium is robust to all possible swap deviations. It's a stronger notion of equilibrium. It's possible to compute in polynomial time, so it's often a reasonable goal to set. Okay, so why not swappergrad? If it has all these great guarantees, why is it the less common type of algorithm in practice compared to external regret minimizing algorithms? I think one answer is the following. You have a classic external regret minimizing algorithm like multiplicative weights, which is going to have a external regret converging to 0 at a rate that is logarithmic in the number of actions. Whereas classic algorithms to minimize swap regret have rates that are linear, polynomial in the number of actions. And oftentimes this is a killer, right? Because modern decision makers choose from very large profiles of actions, right? You're choosing all the possible parameters in a neural network, all the potential strategies in some sort of like multi-agent reinforcement learning, like a plan for every state, these exponentially large sets of actions. And so having this polynomial dependency on the number of actions is often going to make swap regret infeasibly take too long. So back in this 2007 paper, it establishes this swap regret algorithm that asks if we can improve the rate of swap regret in terms of the dependency on n. We answer it in the affirmative. All right, let's talk about our main results. We come up with this algorithm, tree swap, that indeed has swap regret converging to 0 at a rate that is logarithmically dependent in the number of actions. Now, there's a trade-off here. Because we have logarithmic dependence in the number of actions, we now have exponential dependence in 1 over epsilon, like our accuracy parameter. We also have a lower bound in the paper that shows that this trade-off is fundamental. Indeed, if you want to have this logarithmic dependent on actions, you're going to need this exponential dependence on the accuracy parameter. But again, there's all these modern settings where this is a potential trade-off that is well worthwhile, because we're happy with some constant accuracy, wherein, again, we can't get around the fact that we have some exponentially large set of strategies that we're choosing from. And so we need to optimize based on that. As a corollary of this theorem, we establish many other improvements in all sorts of different settings involving swap regret and computation of correlated equilibrium in various game settings. One result of note, corollary of note, is that we establish a PTOS to compute correlated equilibrium in extensive form games. Previously, for constant epsilon, it wasn't even known. All we knew how to do was compute this thing called extensive form correlated equilibrium. Cool, a lot of corollaries, good stuff. So I want to describe the algorithm a little bit with the time that I have remaining. Yeah, what's up?
So I thought that there was a lower bound with polynomial n.
Yeah, okay, so there's the caveat. Okay, so as I introduced swap regret here, I guess there's a slight caveat between what is known as distributional swap regret and what is known as sampled swap regret. So as I introduced it here, we have a learner who is choosing a distribution over actions every single round, and then that is the actual thing that they're submitting. There's also a setting wherein you can have a learner, select a distribution, but then they're forced to actually sample from that distribution and submit that sample, right? That distinction doesn't make a difference for external regret. In both sense, there's only two terms. There's this reward we got, which is going to be the same in expectation, and there's this best fixed action, which is going to be independent of what we play. Swap regret's different, right? Because now our benchmark is going to be in terms of the actions that we played and transformations of those actions. So it's actually the fact that we have to sample, which, so in the Blum-Mansour paper where they have this lower bound, they have a lower bound in that sampled setting, okay? But the thing is, there's many reasons to motivate the distributional setting. Primarily, if you want to compute these correlated equilibrium in these games, you don't need to force anyone to sample. And I think in a lot of other ways, it's the natural thing to consider distributional swap regret, as this generalizes to just general online convex optimization, where we're now doing just linear transformations over, the simplex, things like this. You're getting to further motivation. But distributional swap regret's the good stuff, and we've improved it. So that's what you should take with. All right, I want to talk about our algorithm. If you're familiar with the Blum-Mansour algorithm, you know that there's this kind of important subroutine where we use an external regret minimizing algorithm as a black box in the larger algorithm. We're going to do something similar here, but we're going to use a lazy external regret minimizing algorithm. What does that mean? So what we're going to do is we're going to take our interval of time, t, and we're going to chop it up into m blocks, okay, each of equal length. And what our algorithm is going to do is it's actually going to just repeatedly play the exact same big strategy for an entire block. And only at the end of the block does it update. It's going to look at all the reward it saw over that block, and finally make some sort of update. Then play that action for an entire block, update on all the reward it observed over the block. Repeatedly do this, playing the same exact big strategy over blocks. Why would we do this? This seems silly, right? Because a classic external regret algorithm like multiplicative weights will have external regret converging to 0 at a rate of 1 over root t. Whereas this algorithm, if we plug in multiplicative weights, would have external regret converging at a rate of 1 over root m, right? The number of times that we update it. This seems simply more inefficient, but the benefit is that we played fewer different mixed actions over the course of all this learning. Remember, when we're doing swap regret, we're comparing ourselves to all these swap transformations, and if you look at this history of play, and you look at any swap transformation of it, it must be the case that because in this history we played the exact same mixed action over a block, any transformation will also be constant over a block, right? And that's going to be this key property. Let me quickly describe the algorithm with the time I have left. It's going to constitute a sequence of layers, okay? The first layer, let's just say t equals m to the d, m and d are integers, all right? The first layer is going to be an instance of, let's say, lazy multiplicative weights, right? So that's one algorithm that runs all t rounds, has blocks of size t over m. The next layer is going to constitute m instances of lazy multiplicative weights, okay? So each algorithm runs for t over m rounds and has a block of length t over m squared. The next layer has m squared instances. Each algorithm runs for t over m squared rounds, blocks of length t over m cubed, going all the way down the tree to instances that run for m rounds each have blocks of size 1, not even lazy. And how this algorithm is going to work is that at every single round t, kind of depicted by this vertical line, we're going to query each layer for its recommendation, and we're going to play the average of these recommendations. Okay? We then receive some reward, and we're going to update each layer with a scaled down by 1 over d fraction of this reward. If you're familiar with Blum-Mansour, you know there's this idea where we're going to feed into each external regret instance the proportional weight that we listen to that algorithm's recommendation of the reward. We're doing something similar here. Okay, so what's the swap regret of this crazy algorithm? It's the following, right? There's some sort of action that we played over this block, okay? It's going to have to compete with the best fixed action over that interval of time. There's some action that's played for this block. It's going to have to compete with the best fixed action over this interval of time. There's some action during that block, we'll have to compete with the best fixed action over that interval of time. Going down the tree, that action will have to compete with that fixed action, that action will have to compete with that fixed action, etc. Going for the rest of that layer, as well as all the way down the tree. So the swap regret of this algorithm is the reward of all these pink actions compared to the reward of all these yellow actions, okay? But this difference is going to telescope in a very cool way. let's look at the rewards, the swap rewards of the first layer compared to the actual rewards of the second layer, right? Namely these two terms right here. If you look at the difference of these two terms, you realize that this is exactly the external regret of this algorithmic instance, right? What is the external regret of this algorithm? It's the reward that it got compared to the best fixed action over the entire amount of time that this algorithm was running. So that's exactly what STOC is. These two terms compare to be the external regret of that algorithmic instance. That's an external regret. That's an external regret down the tree, and that one, and that one. It's all external regret, all right? So you got d minus 1 of these layers that are equal to the external regret of these subroutines. Now we're telescoping, so we're leaving one out at the end. And indeed, this is the worst case, single best action every single round, right? But we have this benefit that we scaled down our reward spent to each layer by this 1 over d. So what we lose because of this final term is only a t over d additional swap regret. So if you put this all together, you have d minus 1 layers that get a 1 over root m swap regret. You have this final layer that gets this 1 over d swap regret. As long as m is log n over epsilon squared, as long as d is 1 over epsilon, you get epsilon swap regret in the number of rounds that is logarithmic and then exponential to 1 over epsilon. And that's it. So thank you for listening. I wrote a little blog post on my website explaining some intuition behind how we came up with this. Check it out. Yeah, that's all. Thank you.